Hello, everybody. In today's lesson, we're going to take a look at the mathematics of nuclear decay. And we're going to start here with a graph of N versus T. So just real quick, let's define these variables. On our graph, N is the number of radioactive nuclei. And T, of course, is just time. So we're looking for a sample of radioactive nuclei, how the number of radioactive nuclei varies as a function of time. We know that the radioactive nuclei are unstable and will undergo radioactive decay, so there should be fewer radioactive nuclei as time goes on. And when we plot the results, we see that that's true. So in this example, we're just saying that we have 100 radioactive nuclei at some time t equals 0, and then as time progresses, we see the number of radioactive nuclei remaining decreases as the radioactive nuclei undergo decay. So with that being said, if we try to fit an equation to this plot of N versus T, we do see that it's not linear, it's an exponential decay. We end up getting the following equation. N is equal to N naught times e raised to the negative kt power. So we already know that N here is the number of radioactive nuclei. Let's put that up here, number of radioactive nuclei. T is the time. N naught, in this case, is the initial number of radioactive nuclei. Or in other words, the number of radioactive nuclei at time t equal 0. So then N would just be the number of radioactive nuclei at time t equal t. And then E here is Euler's number. And K, finally K, this is what we call the decay constant. So it's a proportionality constant. And different radioisotopes, different nuclides will have different decay constants depending on their rates of decay. Speaking of rates of decay, if we look at this plot of N versus T, if we were to be interested in the rate of decay at a time t, all we have to do is draw a line tangent to the decay curve. So let's use a different color here and draw a line tangent to our decay curve like that. If we find the slope of this line, tangent to the curve at some time t, we would be able to find the rate of the nuclear decay at that particular time. And because this nuclear decay curve is concave up, we do see that the rate of nuclear decay is decreasing as time progresses. So it would be maximized initially, the initial rate will be the greatest, and it will be minimized. Well, it would be minimized when there are no radioactive nuclei remaining, but we do see it decreases as time progresses. This is significant because, let me erase some of what we've got here, clear up some space. It's significant because we can write an equation for the rate of nuclear decay based on this treatment, where the rate is equal to the number of nuclides times the decay constant k. And so again, we see as n decreases, the rate would decrease, and that's consistent with our graph. Now, this is obviously an exponential decay, so it's a little bit difficult to work with mathematically, and we're interested in characterizing nuclear decay in terms of attributes like half-life, for instance. So what we find useful with nuclear decay is to actually, rather than plotting the number of radioactive nuclides as a function of time, to plot the natural log of the number of radioactive nuclides as a function of time. And when we do that, we get a graph that looks like this. It's a linear decrease. So all that I've changed from the previous graph to this one is the dependent variable. Rather than plotting the number of radioactive nuclides on the y-axis, I'm plotting the natural log of the number of radioactive nuclides on the y-axis. And then the equation for this line ends up being the natural log of n is equal to negative kt plus the natural log of n naught. So this is a y equals mx plus b linear equation, slope-intercept form, where the slope of this line, m, is equal to negative k, and the y-intercept is equal to the natural log of n naught. Now, a lot of times this equation is written in a different form where we subtract the natural log of n naught from each side. Then if you think about what you've learned in math class about logs, the natural log of n minus the natural log of n naught is equal to the natural log of n over n naught equal to negative kt. So this is the same equation, just not written in slope-intercept form. And this is what we will more commonly use in chemistry class. So let's talk a little bit about why this particular graph is useful. And this is in terms of the characteristic that we call half-life, which is the time it takes for half the sample of a radioactive nuclide to decay. Think about what we know for the definition of half-life first off. So let's erase everything except our slope-intercept form here. Oh, you know what? Actually, let's erase the slope-intercept form. Let's go with the second form of the equation we had there, where we had the natural log of n over n naught equals negative kt. So if t is equal to the half-life, t equals t1 half, we know that half of our sample will have decayed. So the ratio of n to n naught at t equals t1 half would be 1 half, right? Here, let's change this so it makes a little more sense. Rather than at t equals t1 half, let's say if t equals t1 half, then n over n naught equals 1 half. So if we plug that into our equation up here, n over n naught is now 1 half, and t is now t1 half. We can simplify this a little bit. So here's what that looks like. Get my pen back. There we go. First off, I'm going to divide each side of my equation by negative 1, like this. So that's negative natural log of 1 half equals kt. Now, the negative natural log of 1 half is actually equal to the natural log of 2. So now I have natural log of 2 equals kt. And remember, t here is t1 half, so let's write that in, kt1 half. And now I can solve this equation for t1 half, where I get t1 half, the half-life, is equal to natural log of 2 over k. And this is an equation that we'll use frequently in chemistry class with half-life calculations as well. And now you see where it comes from. If we plot the natural log of the number of radioactive nuclei versus time, and then analyze the slope-intercept form of that equation, plugging in t1 half for t and 1 half for the ratio of n to n naught, we can derive this equation for half-life where t1 half equals the natural log over k. Okay, so that's just a quick overview of some of the mathematics of radioactive decay. Hopefully this sort of clears up any questions you have about where the formulas come from.